matter says that exactly this. Matter can't be created or destroyed, and what that means in a chemical equation is that a chemical equation has to have the same number of stuff going into it, like the same weight of stuff going into it, those are the reactants, as there are coming out of it, the products. You could look at it as the same number of atoms going into it, reactants, as there are coming out of it, products. And I can demonstrate that to you here. We just need someone who's kind of close by. Let's see. Make sure that's zeroed. Yeah. So if you look here, we'll get Tristan to come look at a number for us real quick, if you don't mind, Tristan. Would you just read off the number that's on here?
97.9.
Spectacular. All right. So I'll try and do this so you guys can read it, but what I'm showing you here is that even though in this chemical reaction inside here, something new is going to form, right? If you look at it both right now, they're both clear liquid. So something new is going to form in here, and even though something new forms in there, what we'll see, or what we should see if this is true, is that what goes into it, those chemicals, weighs exactly the same as what comes out of it, the chemicals that they're going to produce, even though they're going to make something that is there or is not there currently. So if I hold this out here for you guys, let's see if I can get this right. So you guys see it well enough. So it's the one that we did yesterday where that turns bright yellow for us. So you can see the new stuff being formed. I'll pour this all in there. So clearly something new formed inside of there. And Tristan, would you come back up and take a look at the mass for us?
97.9.
Exactly the same. So what I'm trying to illustrate is that when chemical reactions happen, they are balanced. The amount of stuff that you mix together weighs the same as the amount of stuff that comes out of it. If you think about it in real life, it makes sense, right? If you put a pound of rocks together with a pound of dirt, how much is it going to weigh? Yeah, because you automatically know the law of conservation of matter. If you add these two things together, the result, the mass result of that's going to be the same as those two things separated. And it kind of works like this. When we're balancing these things out, a balanced reaction is kind of like a teeter-totter, if you think about it that way. And that is that on the left side, we've got reactants, right? And on the right side, what are those things called? Products. When a reaction is balanced, literally what it means, Todd, is that the reactants and the products have exactly the same mass. So you could put it on like a teeter-totter or a balance, and it would balance out. If you've got one of these things that weighs more than the other, it's an unbalanced reaction, and that's when we've got to do some work to balance it. So that's our plan for today. That's what we're working on. And there's two ways to think about it, this balanced chemical reaction. Balanced chemical reactions either have to have the same mass, you can think about it in terms of weight on both sides, or they've got to have the same number of atoms. Either way, it's the same thing, if you think about it. Because if you've got 2 pounds or you've got 10 quadrillion atoms on either side, they're going to weigh the same amount. So there's only a couple rules for balancing these things out. And we'll go over those rules here. Ready for the next bit? All right. Jordan Dimmick?
So, when we did the lab last week on Friday, when we were in the magnesium turned into dust, but it seemed like some of the dust went from there, and a piece of magnesium burning up, so it would still be the same weight.
Yeah, do you remember that there was smoke released in that reaction? So if you could collect the particulates from the smoke and weigh it with the magnesium oxide that was left behind, it would weigh the same. Same is true for like a thing, if you have a wood stove and you throw a piece of wood in there, if you could weigh the ashes and the smoke that come out of it, it would weigh the same as the log that you put in there. You'd have to capture it and then like somehow solidify it or get the particles to stick to something. So, moving on. The rules for balancing these things out. This is the first one and this is the biggest one. And here what we're talking about is the word coefficient. Do you guys from math class recognize what a coefficient is? Okay. So, what about this? In your group here, your table group, if you could do this, x plus 6y equals p, can you identify in this equation, in your group here, what the coefficient is, or what a coefficient is from this problem? Let's take a couple. Back up here, and I ask you the question, what's the coefficient here? It's what? You're close, but not quite. Tristan already identified himself as not good at math, so I'm not calling on Tristan. Mia? 6. Coefficient is the number that comes in front. And when there's a coefficient, what math operation are you supposed to do between the 6 and the y? That's a multiply thing, right? So that's telling you there are 6 y's or 6 times y. So it's important we keep that in mind today because we're going to be changing and manipulating coefficients. And it's critical you remember that coefficients are multipliers. So we'll come over to here. If we come over to this side and take a look where it says the rules for balancing equations, the first one and the most important one you got to have down is this, that you can change the coefficients, but you cannot change the subscripts. And we'll go over what the difference between those two things are. As you're looking at this chemical formula today, there is a coefficient in here and there are subscripts in it too. What's the coefficient in this thing? 6. What are the subscripts in this thing? Okay. So as you're looking at this piece that's right here, a couple things to notice. When you change the coefficient of stuff, like if we were to change this to a 5 or to a 3 or 2, this tells you how many of these molecules there are. C6H12O6 is a sugar, like glucose is the name of the sugar that it is. And this 6 in front is telling you that there are 6 things of glucose, so 6 molecules of glucose. When you change the numbers down here, you start to change what the chemical is that you're talking about. And I'll give you an example here. When we did the lab, we dealt with a chemical that is... we dealt with 2 chemicals. One was H2O, which is, and one is H2O2. Do you remember what that was? Hydrogen peroxide. So when you change the numbers that go below, you actually change what the chemical is, these subscripts. But if you put a number in front, like that, you're changing how many of these molecules are here. And remember, it's a multiplier. So if I've got 2 things... well, we'll come back to this. So subscripts and coefficients are what's there. So far, so good? All right. The next slide is just like nothing to write down here. It's just some pictures to help you visualize the difference between subscripts and coefficients. Go ahead, Luke. So when you see a letter like this, that represents an atom from the periodic table, right? If there's no number written down here, what's the number that's really there? It's a 1. So when you see the letter C, that represents 1 atom of carbon, right? When you see the letter O, that represents 1 atom of oxygen. When you see an O2, how many atoms of oxygen are we talking about? 2, right? O2 means 2 oxygens together. When you see a CO, that's 1 carbon and an oxygen. When you see a CO2, how many carbons are there? 1. How many oxygens are there? 2. And then you can look at this picture because this is kind of where it helps you out. If you've got 3 CO2, that means you've got 3 molecules of CO2. So in 3 CO2s, how many carbons do you have? 3. How many oxygens do you have? Okay. So here's something for you to do in your group for me here. I'm going to have you figure out the number of atoms present in these things that I'm going to put up here. So we're going to use these 3 chemicals. So in your group, would you please figure out how many atoms of each thing are in these? So how many atoms of PB, how many atoms of N, how many atoms of O, and same thing across here. I'll give you guys like 2 minutes in your group to put things together for practice here. So there's the equation, and at your table, if you wouldn't mind, I'm balancing out. That's not going to show it, but balancing out this chemical equation. How close you guys were, if you got it. So as we look at this first one, PB is lead. So how many leads are there? 3. Because remember, when there's not a number down below, there's like a hidden thing, and a hidden number 1. And we said that this acts as a multiplier, right? So if you want, we can draw these things out, and I'll show you. But it says PbNO4. So if we've got PB, that would be a PB, an N, and then 4 O's to go along with it, right? So O, 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 O. It would look like that if we had one of them. But instead it says we have 3 of these things. So we've got it like, that would be 2 of these things, and you can start to count stuff up. But you can see at this point that if we had a third one, we'd be at 3 leads. How many nitrogens? 3. How many oxygens? 12. It's a multiplier. One way people go wrong with this sometimes is they forget that this subscript applies just to the letter that comes in front of it. So they forget. Todd and Luke, can you guys quit, please? Yeah, we're kind of to that point. Hey, Luke, you're going to be the one that goes to an island this time. So now it's Luke Island. So if you've got this oxygen is what goes with the 4. This 4 doesn't go with the N or the PB. It's just the oxygen that's right there. So, and this is a multiplier. If you work your way through here, how many carbons do we have? 36, because it's 6 times 6. A little bit more tricky math here. How many hydrogens do we have? 72 total, and then 36, again, oxygens. And then finally down here for hydrogen peroxide, how many hydrogens? 8. And oxygens? 8. Okay. Why that's key is because that is what's going to allow you to count up and balance these chemical equations. In these things, you're going to be asked to figure out how many specific atoms there are on one side of the teeter-totter, and then add in coefficients that make sure they're exactly the same amount on the other side of the teeter-totter, or on the other side of the scale. So that's the gist of this. And if you can do that, honestly, like figuring out how many atoms are where is the hardest part of this. After that, it's just like a little bit logic, or if logic's not working, like a little bit guess and check, and you can get it to work every single time. So we are onto the steps to balancing chemical equations. A big chunk of text is about to pop up. You're not going to write it down. We're going to write down just a selected bit of it after I kind of read it to you and we talk about it for a minute. So you don't want to write anything down yet. Make sense? Ashley's already writing stuff down. She is on it. All right. So, like I said, big chunk of text, nothing to write down. Tristan, what are you doing? Sure. Okay. So when you've got a chemical equation, and this is a chemical equation right here, you guys should be able to, number one, tell me what type of equation that is, like what type of chemical reaction that is. If you know how to tell what type of reaction that is, would you hold your hand up for me, if you can figure it out? What are we talking about, Keon? Single displacement. Very good. You've got a compound here and an element there, so it's a single displacement reaction. So the first thing we have to do is to start with the chemical formula to check to see if it is already balanced. As in, does it have the same number of moles? We'll talk about moles as we go through this, or atoms. We'll use atoms on each side. So we're going to take a look. We'll start with the equation. We'll work our way from the left to the right. If we look at aluminum, how many aluminums does it have on the reactant side? 1. How many on the product side? 1. Aluminum's balanced. So far we're thinking like this is a balanced equation. How many bromines on the reactant side? 3. How many on the product side? And we can stop there. We don't have to go further because our teeter-totter is not balanced. If we've got 3 on one side and only 1 on another side, it is unbalanced. It's not a balanced chemical reaction. So the first thing I'm going to have you write down is step 1 in balancing a chemical reaction. Check to see if it is balanced. Some of them will drive you nuts because they're balanced from the start and you're trying to figure out how to fix it, and it just doesn't work because they're balanced from the start. So start by checking to see if it's already balanced. And if you want, you can use, this is one of St. Clair's handy-dandy hints for balancing chemical equations, which are famous, world famous. You can use Mr. St. Clair's world-renowned, highly famous, super useful flowchart. Is it balanced? Yes? You're done. If it's not balanced, you got to balance it. You're welcome. So, you can write that down. You can take a mental image of it if you want, whatever you're going to do to help you out. But if it's balanced, that's it. You're done. This thing, though, we've already determined is not balanced. So we're going to move on from that flowchart on the no side, the no it's not balanced part. To balance it, here's what you're going to do. You are going to start by, this wants to be your next step. This would be step number 2, right? Start by finding the atom with the largest subscript, like with the largest number below. And in this case, you can clearly see that's bromine. It's the only one with a number, and its number is 3. I know. Good on this slide? Okay. Why are we starting with bromine? Biggest subscript, that's right. So for flipping this over, again, big chunks of stuff here, we're just going to write down selected sections of it. As it says, as we identified, there are 3 bromines on the left. So in order to make there be 3 on this side, we either have to add a subscript down here, or in front of it, we've got to add a coefficient. Do we need to add a coefficient or a subscript? Look back in your notes. One of those you can add, one of them you can't. We can only add coefficients. We can't change numbers. If you change numbers down there, you change the chemical that it is. So if there are 3 bromines on this side, what number do we need? What coefficient do we have to put in? What multiplier do we have to put in to make there be 3 bromines in? 3. And you can see it down here. A 3 in there. And now we can take a look again. As you guys catch on to this, it'll be a little simpler for you. But every time right now you put a number in, we're going to reassess if it's balanced. So as we take a look, aluminum, how many on the reactant side? 1. How many on the product side? Okay, that's looking good. That's balanced. Bromine, how many on the reactant side?
3.
How many on the product side? 3, because we put that there. So bromine's balanced. And then the last thing, potassium. How many potassium on reactant side? And how many on product side? 3. Now it's still unbalanced, and we've got to add in another coefficient. And that's what we're talking about here. Potassium is now unbalanced. It has 3 on the right, on the product side, but only 1 on the reactant side. Can you guys already figure out what to do here? Okay. All you got to do to balance potassium out is you've got to put a coefficient in front of it. Good try, though, Todd. So now, with that there, we've got 3 potassiums on that side. We've got 3 potassiums here. We've got 3 bromines and 3 bromines, 1 aluminum and 1 aluminum. And that is a balanced chemical equation. And that's how you do. That's the steps to carrying that thing out. That's what you do. What's that? It really isn't that tricky or tough to do. We'll do another example here for you. So this one. As we look at it, and you follow along in your notes here, which one are we going to start with? How do you know? Biggest subscript, that's right. So look, as we're doing this, what coefficient are we going to have to put in? Can you focus here so I don't have to just be working on that. So as we look here, for the rest of you guys, what type of chemical reaction is this? Synthesis, very good. So we're starting with the one with the highest subscript right there, so the 4. And how many phosphorus are there on the reactant side? 4. We need to make there be an equal number on the product side, right? What coefficient do we need to put there then? 2, because it's a multiplier. And I think that's what we're talking about here. So highest subscript first. This thing is not balanced out. So we've got to make it balanced out. Which means we're putting a 2 over there. The next thing we can do is we can look at the oxygens, because those are what comes next. How many oxygens do we have on the reactant side? So multiply, so we've got 6. What number are we going to have to stick in front right there to make it be 6? 3. Stick the 3 in, and then we're in business. It's a balanced chemical equation. That's all there is to it. You do not have to put a 1 in here or anything like that. You can just leave it blank. You don't need a 1 or a dash or anything like that, or a 0. You can leave it blank. So a couple more of my famous helpful hints to help you balance chemical equations. You ready for these? Perfect. That is the correct answer. So these hints are actually probably the most helpful ones there are, because these things will drive you wild sometimes. So take it one element at a time. Sometimes you look at a chemical equation and you try and balance it all in one step, and it's almost impossible to do that. And it gets easy to get confused or turned around or kind of lost. But just do one thing at a time. It's going to make your life way easier. Second thing, and this one gets a little star or a highlight or whatever beside it, because this is kind of critical, and that is that save hydrogen for next to last every single time, and then save oxygen for last every single time. And that's because these things usually, or will sometimes appear in a chemical reaction in more than one place. Like you might have 2 reactants with oxygen in them, or 2 products with hydrogen in them. And it's hard to do it that way, so it's just helpful to save them for last. And then the last tip, which also should get a star, an underline, or whatever beside it, is that you'll come across a couple of these, and maybe even today we'll come across one, that as you're balancing these things out, you get to a spot and it's impossible for you to balance it, because there's like an odd number of oxygen or hydrogen on one side and an even number on the other side, and you can't get it to go. It's just not going to work. So what it says, if everything balances out except for hydrogen or oxygen, double every single coefficient that you've written down. So this is a key part. You want to make sure you write that part down. If everything works except for hydrogen or oxygen, double every single number that you've already written down. How are they supposed to go? But on the front side of this worksheet, which you get online, balancing equations number 1, there are equations on here. There are some questions to handle. The equations at the bottom, you don't have to balance. It's just asking you, is it balanced or not? On the back side are the 10 that you've got to balance. So there's a front and a back, with the ones on the back being the one you got to balance. We'll do